Today we will have Xinyu Zhang from Jinko Solar. Xinyu is an old friend to Spray. I think some of you already have some collaboration project with him on different topics. So Xinyu finished his undergraduate in here, Spray, UNSW, and then he moved to ANU to finish his PhD. And then in 2016, he joined Jinko Solar as the director of research and development. Now he's in charge of the research and development of Jinko Solar. Today, Xinyu will try to share some recent research progress in Jinko Solar and some industry insights with us. If you have any problem during the seminar or after that, you can just leave your question on the chat panel, or once you finish, you can just pop up and ask the questions from your side. So now over to you, Xinyu. Thank you for your time today.
It's my great pleasure to be invited for this seminar. Glad to hear this is the first seminar of the year. It's actually my first online seminar. And I saw many familiar names on the participant list, so I guess we can make a relatively relaxed or flexible kind of form. So I try to finish my presentation a bit quickly so we have enough time for some free discussions. So please allow me to share my screen. Okay. All right, so I during this seminar, I want to give some updates on the latest research achievement at the R&D center of Jinko, and also I'm very glad to have some industrial innovation discussions with you guys, and just to talk about what we are doing and what the actual the key features of our work. Well, at last, we'll go through some questions and answers. Next page, please. A little bit about myself, but many people are quite familiar with me. I'm currently working for Jinko Solar, which is one of the largest solar panel manufacturer. And we are also a integrated company. So we work on manufacturing from solar ingot, from silicon ingot into the solar panel. So all the part, and we have a separate company who's working on the power generation as well. I myself graduated from AU, like Kevin just mentioned, and now I'm working on both solar cell R&D and wafer growth R&D. Yeah, next page. Okay, so the main three topics I've covered. Next page. Here, I just want to briefly talk about our main research interest, which is to develop the TOPCon structure solar cells. Although I know there are many names in the academic, and basically most of the commonly understood name is actually passivating contact technology, but TOPCon is commonly used in the industry. So when you hear that, don't be surprised that any similar structure will be called TOPCon. For us, we are trying to push this new generation of technology into the production in a large scale. Currently, we have 1 gigawatt of capacity for TOPCon cells, and we are aiming to increase this capacity furthermore. The key features regarding this cell structure is it has a very good efficiency. Now we are seeing that average efficiency is over 24.5%, which you will see later. And the high VOC, as well as the very good service passivation is very good, very important contribution to the high efficiency. The idea of TOPCon, we consider that's similar to another very hot topic, which is heterojunction solar cells. These all approaches like trying to isolate the metals with the bulk, so that the passivation at the contact region can be further improved. But there are a lot more than that. So the efficiency increasing is beyond just the simple concept, but also the many other optimization process. Next page, please. So the key technical aspect of this TOPCon cell production TOPCon cell is firstly the passivating contact technology, allowing a very good G0 of the host device, which, well, especially at the surface region without the contact, the G0 can be as low as 2 femtoin per centimeter. So which is allows the possibility of high energy conversion. And also the metallization system is a new thing to the industry, although we are still using the screen printing, but this new structure is allowing semi-isolation between metal and bulk. I won't say it's completely isolation because that's not true. It's more like a contacting in very small area, areas, and also in a special phase. So the ohmic contact in the poly region can be guaranteed to be very well. And also we can still enjoy the benefits from screen printing, which give us a lot of advantage on being in a mass production state. Well, the optical optimization is also important because the front side we don't have the poly, so we can still keep a very good anti-reflection at the system at the front. At the back, although the poly is absorbing some light, but by doing some proper control, we can still maintain a very good bifaciality for this solar cell. All here I need to mention all these solar cells are bifacial. And we are now looking at bifaciality is closing to 90%, so that is good enough, although there is still room for further improvement. Well, for the N-type TOPCon technology, we also benefit from the bulk material improvement. For N-type wafers, now we can achieve large scale, high throughput, but also very high lifetime quality for the N-type wafers. Well, at the same time, for the LID problem or LETID problem for P-type wafer will not exist anymore for N-type product. So it's a very big advantage. Next page. Here I present some latest results. So last year in July, we have achieved the large cell solar cell with using TOPCon structure to achieve 24.79%, which was the high efficiency during that time for large cell, for large size TOPCon. And so this is achieved from one champion cell from a pilot line production batch. So it's not particularly designed for laboratory. It's more like one of the best of a very good batch. And next page. Next page.
Sorry.
Thank you. So 1 month later, we further improved that based on some metallization improvement, and the efficiency has improved into 24.87. And after that, we did another small improvement. So only the figure is slightly higher, which currently at the highest efficiency we can achieve is 24.9. So I think early by half, the first half of this year, I think we can achieve more than 25. That's the new target, which I will mention later. Next page. Yeah. Oh, again. Next page. And one more. Yep. And this is the highest multi-crystalline silicon, or we should say is casting growth wafers the highest efficiency we can achieve is 24.4. You can see it's pretty much the highest one we can achieve by casting materials. And I think it's gonna take a while to break this record, but we'll try. Yeah. Next page. Yeah. Well, in terms of the loss analysis, we can see that we have done very detailed loss analysis, and including some calculations and for the champion cell batch, and we can see that the major power loss is still at the front grid shading. It's challenging to further improve the front grid shading, but also it's possible. So when we have the idea of reducing the metal coverage areas, and also further better optical control, we do have confidence that to improve the light absorption, to reduce this power loss significantly. So this it's a good analysis and also a good news. And the second biggest loss is from the base collection loss. Well, here we also include the parasitic absorption. So here we need to further improve the poly structure at the back, and also the material, as well as the light absorption in the poly region as well. So from the left graph, you can see at the blue losses regions, there's still room for us to further improve, and we do have some solutions for this. So please be patient, and we may give some updates later. Maybe next time I give the seminar. So next page. Here, so it's like a summarize what we try or what we are targeted to do. So the 4 atoms with red column is showing that the major research direction for us. So P+ contact recombination need to be further improved. It's not poly-relevant, but it's also very important. And also the lateral transportation of the positive carriers, and also the non-contact recombination regions need to be improved as well. And you can see that a lot of contribution come from the P+ region, so which is also very challenging. So that's one of our major research direction in the near future. And also, I think the recombination at the of algae and radiative can also be improved as well. Next page. Here, I give some examples of our latest improvement. First is the doping activation technology. Oops. Some back voice. Yeah. So we are trying to use some technology to improve the dopant activation rate, or the possibility of the dopants to be activated. So now a new technology allowing us to use less amount of dopant, which about 80% of the original doping of the dopant, but achieve rather the same surface doping concentration. So this will allow us to get well, firstly the throughput and also the performance is improved. You can see from the PL image on the bottom of left, and so you can see that the light the PL count has increased a lot. Well, as well as when we do the EQE and the IQE comparison, we see that the blue loss region is also improved. So this allows us to have some efficiency increase close to 0.0%. Well, next page. Another very good example of the industrial level technology improvement is the metal region. So we can use PL technology to extract relatively accurately of the J0 metal. So it allows us to improve the technology at the same time to understand how much we have improved. And while the finger width control is another important research topic for us, we have now able to find a wafer the finger width close to 25, so which is very thin. For mass production, it is also possible, but normally at the mass production level, it is still sitting around like more than 30. So there's still a very nice gap that we can fit, which will definitely improve the efficiency, as well as the valuable or expensive metal consumption. Next page. So here I presented our near future target. Now you can see we're sitting at 24.9, and by certain recombination, loss improvement, and also some other optimizations, our near future target is to achieve 25.1. And we do have the confidence because several technology has been proven to be working, and this is more like to do a lot of optimization and do enough amount of experiment to achieve a very good result. Yeah. Next page. Here we mentioned some of our mass production situation. So we have a mass production line, not only one line, but 1 gigawatt of capacity for TOPCon. So we have seen that the improvement of the average efficiency, the efficiency distribution, and also the yield rate is improving very fast. Because TOPCon is unlike heterojunction, it's more like it's a combination of several familiar process, such as the diffusion. Although instead of only phosphorus, now we have both phosphorus and boron diffusion, but still relatively familiar to the production people. And also we have simplified the process flow a lot, so it's only a few steps more than the traditional PERC production line. So everything can be controlled relatively well. I have to say that production people, in terms of the production figures, then the production operation people are doing much better job than the R&D people. So it seems like the figures are showing very looks very beautiful. Yeah. Well, but for us to further improve the efficiency is quite important. So our I probably will say midterm target will be to achieve more than 25%, which has been proven to be possible in theory. And also we know that the highest efficiency for N-type TOPCon is about 25.8. So for mass production, it is the origin of the confidence. Yeah. Next page. Yep. So here I mentioned several of the major challenges and how we overcome that. While the boron diffusion has been improved by relatively much improved fabrication tools, and also the recipes has been modified a lot from what we actually started. So to make the production stable is actually more important more important than one batch to be good. So that's we have done many work on this. While the tunnel oxide growth used to be a very important but also challenging thing, but now we have managed to achieve very stable oxide growth with special tools. So although the thickness of the oxide is below 2 nanometer, but it can still remain to be repeatable and reliable. Yeah, that's pretty much the the bottom line of the production. The wraparound removal, Jinko is using some our own sequence and technology, so we never feel there's an issue of this. So yeah, although I know there's some people in the industry saying it's quite challenging, but for us, we find it's okay, and the yield rate is well proof of this. Well, as well as some others like the polysilicon layer optimization and firing paste. So there's many small optimization, probably not very high research values, but it's very important for the production to be giving the best product to the customers. Yeah. Next page, please. Oh, sorry, I forgot to translate this page. Well, anyway, that's our roadmap for achieving 25.5. Is more like a midterm and a little bit long term, but I think it won't take very long because now we think that 25 is definitely within 2 years. So maybe things will go faster than we expect. So let's see. So the industry is moving very fast. Like, yeah, we may cover them maybe during the last session. Yeah. Next page. All right, a little bit of our module technology. So now in terms of the high-end product, we consider some residential market. I know that in Australia, residential market is actually a very important part of the share, but globally looking, residential is still a relatively small part. But for high-end products, very important because we need a very good premium. And so that we need to provide, combine several good technology together for the residential, such as the multi-bus bar, and also we have the gap reflective coating, and also Jinko's special technology, Tilling ribbon, TR technology is also used so that it looks very uniform and all black. And combined with high efficiency of TOPCon, then we can give very attractive residential product. But for the grid type of product, TOPCon is also very good because of the low degradation and also the higher power generation rate. Next page. A little bit more too. So exit is already early last year's result. We can provide module power is more than 610. And the module efficiency is about 22%. That was the best result we can achieve last year. I think this year is even higher. But for very large size of modules, not everyone like it. So it's the most popular product at this stage is giving the module power around 500 and a little bit more. So that's pretty much the best region. Yeah. Next page. Well, here is some reliability result. It was a bit quick, so I did not provide a complete analysis. Here I'm just giving some examples of our comparison result with heterojunction modules. And we can see that from all expect TOPCon technology, well, here the HOT is the Jinko name for TOPCon. So you can see that from the DH dump heat, it performs much better than any other modules in the market. Well, yeah, I think a mainstream product, I would say. And also for all other reliability tests, N-type is showing very good performance, better than most of other products. Next page for both front and back. All right, so and then we goes to next session. So I talk about some, well, I found this topic is always interesting to some students. So they want to know what is going on in the industry. What are the R&D work in the industry? So here I mentioned a little bit of our key characters that is for the R&D in the industry. So firstly, our project or our research will need to be target and result orientation. So it's very clear. So the company is paying money for us to achieve a higher profit rate. So of course we need to focus on the target and focus on the result all the time. And also a second character is the timing. Because we need to have certain, maybe the technology is good, but if you don't do that in a good time, then it probably not ready yet, or it is already out of date. So timing is also combined with the target. So so all our work is based on a certain requirement for timing. So it's another important character of industrial R&D. Well, the third character is repeatable and reliable. So all our result is not showing this champion sales, although we are very happy to achieve record champion sales. But what's more valuable to the company is to find a reliable way to improve the production. Well, and also the last character maybe sounds a little bit surprised is step by step. Some people ask whether all companies want things to happen very fast. Yes and no. Well, step by step and small changes accumulating is sometimes quite important, because we know that things can. So we have a certain roadmap to go forward, and also we know that this small step is can be well controlled. So it's also important. All of our work is it's very difficult for us to push to the production with the efficiency increase of more than 0.2%, which is too big. So normally what we do is we do small projects, and one by one, and maybe each one only give efficiency increase by like 0.05, something like that. So small is good sometimes. And next page. So here I also give some examples what we're doing. So what we're doing is we actually do a lot of loss analysis. So a lot of big changes come from very detailed analysis. So they all come from small part. So sometimes we might have surprise when we work on certain small project, and it turns out to be very good. And then, we're definitely very happy that. But we will never be impatient about if the project is too small. So anything can bring that surprise. So we focus on a lot of detailed characterization and also small projects. And also the continuous observation is very important, because once you see something repeated all the time or several times, you might find some clues. Many projects are triggered by such observation. So when we recruit people to for us to working for us, a very important character we're looking for is the ability to observe and to look for to find the story back at the back of the small changes. Yeah. All right, next page. And here I summarize some key conclusions for my work and for many other R&D people's work. So first, don't be afraid to be the first one. And many things you will be challenged. Say that if no one is doing that, is possible, it's not good enough. And that's true sometimes. But for R&D, what we are dealing with is always is like the first thing. So it might be good and might be bad, or it's but don't be afraid to go towards that way. And the second second sentence I want to share is don't insist secondary deductions. So what I mean is here, so when we have certain assumptions or when we have certain observations, and we normally give some assumption, give some deduction or conclusions, and that is a secondary deduction. But if you insist on things like that, you will lose the the process from the first evidence to the secondary deduction. So we find I have many bad examples that we insist, but eventually we find out maybe the original assumption is not correct. And then we figure out ways to overcome that. Well, the third sentence I want to share is, well, when we talk about theories versus practical findings, so it can be complicated. Sometimes we believe, well, of course, we all learn from the theory, we all learn the physics. However, sometimes the practical findings we give you a result against the theory. So it's more like it's always a battle between each other. But for us, we care about both. So if we find some practical findings that is against the theory, it might be just because the assumption is not valid anymore. So at this stage, we need to be very careful and to look for the potential changes and potential new things, and some innovations may generated out of this. Second page. Well, yeah. Next page. Yeah. Here I give example of I think a thinking change, I would say. So traditionally, people think N-type wafers are more expensive than P-type wafers. And if we insist that, you will lose a lot of opportunities. But we need to accept the fact that the world is changing. So a lot of changes has been brought into the industry, such as, well, traditional P-type was boron doped, but now due to the LID and LETID degradation, many manufacturers now are switching to gallium doped wafers. So there is an important figure that is during the wafer growth, the separation coefficient. Well, traditionally, it is true that boron is larger than the phosphorus, so the boron is easy to grow in a fast way and in a large way. But now, because it has switched to gallium, so since the story has turned around, so the phosphorus has a higher separation coefficient than the gallium. So if we are making larger and larger wafers, so that means actually N-type wafers are actually easier to grow than the P-type wafers, especially when the size is big. So now we see that both the gap between N-type and P-type wafers, the relative cost is actually reducing, and also the N-type is becoming large size friendly. Well, at the same time, the RV, the variation of the resistivity is also becoming more uniform. So it's a very good story to very good lesson for us to learn that that sometimes we should not believe or trust the secondary deductions all the time. You should think about the original evidence, original theory, and all the time to look back to see what has changed. And next page. Now I have want to move the last session. So it's actually a more like some open session. So I prepare or I think of a few topics that I think is popular or hot in the industry, but maybe you guys have different opinions. So I don't know. So Kevin or next, what do people think? Shall we? Well, that's not relevant. Yeah. Okay. So shall we start with some questions, or do I cover this topics first?
Let me have a look if we have any question from.
Actually, no question yet.
Okay. Maybe you can talk from your side first, and then. Yeah.
Sure. I'll probably just cover briefly. So the wafer size, you will see that on the news that the wafer size is growing day by day. So the most popular size at the moment is 180, well, above 180 millimeter, and another competing size is above 210. So well, eventually the wafer is going bigger because so that we can have bigger size of the module. so that the overall cost of the balance of the system can be reduced. So eventually it is the customer who decide what kind of size we want. Well, if the wafer is too big, it may not be good because the installation cost can be increased. So it's still in a balanced state that, so which is the best size, wafer size. But from a production point of view, for wafer growth, the large size wafer is not a very big problem. The growth rate may be slower, but eventually the overall cost can be covered. And for the solar cell fabrication, the big size technology has improved a lot. So from the two point of view, it's we have more and more mature tools. From module point of view, it's actually even easier than the cells, so it's not a big problem either. So eventually, as a result, the wafer size is growing. Second topic I want to cover is technical roadmap. Many people saying that PERC is no longer the best technology anymore, and I think the industry cannot believe that, although PERC is still the most profitable product, but now everyone is thinking of transition to a better technology. So what I mentioned, the N-type TOPCon is probably the hottest topic in the industry because it's very similar to PERC, it's easy to upgrade. And another important technology is heterojunction. It's more expensive and the investment is high, and the efficiency is quite promising as well, but it's hard to say which one is higher or not. So Kevin, please go to next page. Here I give some opinion from my point of view. So heterojunction has a relatively long history. It has been developed for several decades. So the efficiency, well, when we look at only the highest efficiency is staying at 25.1% for pure heterojunction for a long time. So we see that it's a little bit saturated, but things may change, well, because many people are working on that. From our point of view, the TOPCon is a relatively new technology, although this passivating concept has a long histories, like back into 1980s, but the actual development of the certain structures only started like in the 2010s. So, but the efficiency increase is quite rapid. Now we are looking at highest efficiency staying at 25.8, and it's also been staying there for a while. But we do think it has a very good potential to achieve high efficiency in a production state. So I think both technology has their advantages and disadvantages. So it's hard to say which one is better at this current stage. Yeah. So please back to the last the last page. Well, the next topic is the industry-academic relations. I think it's a complicated topic, but from my point of view, for single junction solar cells and using silicon, it has been quite a long time. And we all see that the theoretical efficiency is sitting there. So the chance of breaking this theoretical, the limit is, I think, is very, very small. And although we talk about the tandem, but we have to face that the production need certain solutions. So instead of device optimization, now many attention has been switched to new materials and new process. So I would say it's creating, actually there are more chances for industry and academic to work together. But the topic chosen need to be very careful and important. Yeah, I think for us, we have many new projects, quite new material relevant. So I guess in this point of view, actually academic is doing probably in some level better job than the industry. So we do look forward to work with academic for many novel topics, including new materials. Pretty much covered all I have prepared for today. Thank you guys for listening online, and open for questions for sure.
Yeah, thank you, Xinyu. A lot of interesting result and insights from the industry perspective. As Xinyu mentioned, he want to open the discussion with some hot topics in PV industry. I think some of our colleagues may also have some thought. So if you have any question about, in regard to the question Xinyu just presented, or the topics he threw out, or you have new topics want to discuss, please just unmute yourself and ask questions.
Hello, Xinyu. Can I ask a question here? My name is Alison.
Sure.
Yeah, so first of all, thank you so much for the informative presentation. I have really learned so much from it. But at the same time, I was also very curious about when you were talking about the special equipment Jinko used to grow the ultra-thin interfacial oxide during TOPCon fabrication. Well, from my knowledge, it seems that we have two common approaches to grow the oxide, either thermal way or chemical way. I wonder which approach is Jinko using, or could you elaborate more on the special equipment, as you said, to grow the oxide?
Well, thank you for the question. We won't officially abandon any roadmap or any approach, but currently the best working option for us is the thermal growth way. Mm-hmm. When I say the special is because, you know, very control of the heating environment is the key, because you can achieve certain good oxide by certain areas of the tube that is not good enough. What we want is the whole tube to be uniform and good. So there are some technology that has input to guarantee that, but still a thermal way,
Okay. All right. Thanks a lot for the answering the question. Thank you.
Xinyu, can I ask a question? It's Alison here. Hello. Let's put the video in. So thank you very much for the talk. And I've actually got two questions. Firstly, with bifacial modules, what fraction of production is Jinko planning for bifacial modules?
I think it seems you mute yourself.
Oh, can you hear me now? Yeah. Hi, Alison. I think it's a very good question, but maybe I was misleading a little bit. So for bifacial cells, we have switched to bifacial cells for all our solar cell production. But for bifacial module is more like a order based on orders. So for the modules, it doesn't matter too much if you do monofacial or bifacial. Is according to what the market react. But currently we have to see it's more like towards in half from a general figure. But some regions still prefer monofacial. So the general trend is bifacial modules will be more popular in the future. But by what speed, it's hard to say.
Yeah, because when land is very cheap, the value of bifacial becomes much lower. Like if it doesn't matter how much the land costs, you may as well just cover the whole land surface with modules. So imagine in countries like Australia, when you're putting a whole lot of solar farms out in the desert, or in the US, then the value of bifacial might not be as large as in some other areas.
I think the consideration, well, the land use is definitely one of the consideration, but also others like they have. So I do think they're still in a state of lack of research on the bifacial performance, because we do see when we compare monofacial and bifacial, you can see many differences, such as even the working temperature of the wake light response. And these are all very important figures that, well, for the solar farm owners to consider. So it's whether it's a theoretical that way, or it's just due to different, graphic locations. It's hard to say because still lack of research. But in general, because the price difference between bifacial and monofacials are very similar, they're actually sitting on the similar price per watt. So in that kind of situation, many people choose bifacial, especially for solar farm. But for residential, it's a bit different because many people want their panels to align on the roof, while very closely with the angle. So monofacial is still, I think, is still a good option. So in general, I think what we are looking at is more like for, well, in the future, the grid owners will prefer bifacial more. So we have very cost-efficient product for this type of application. But for residentials, we might have some high-end monofacial kind of like option, so that you can choose and even customize. So to guarantee it's looking nice on the roof, I think it's very important. Yeah.
Karen, can I ask another question?
Yeah, sure.
So Pierre Verlinden was asked fairly recently whether there would ever be a situation that modules got so cheap that the cost of transporting the modules to Australia became a significant fraction of the solar farm cost. In which case, because the glass is the heaviest component and the most space consuming, or the glass in the frames, space consuming components, that the value proposition for companies actually importing cells and making modules in Australia may improve. So I was wondering what your thoughts would be on that.
I think it's a very interesting opinion. I do think because I was not involved in the transportation logistic too much, but last year is a different situation because of the pandemic. Actually, the transportation cost has increased a lot. I mean, a lot. So I realized that it's actually a very big part of the cost. Although some customers choose, to pay for the cost by themselves, but there's still many others who prefer to include the cost as well. So I think, yeah, so that's very important kind of situation in the future. So how to minimize the transportation, or even how to well control the logistic. I think it's a lot. I'm not expert in this, but I think there are some solutions for this. Local factory is kind of one of the result of this consideration. So we have a factory in US, and so it's that's because of, if for large orders, it's important to have the local warehouse, and also to save the transportation of the module, and rather solar cells are much easier to be transported. Yeah, so yeah, I think it's a complicated question and need to be further analyzed. Yeah.
Thank you.
Thank you, Alison and Xinyu. Is anyone have questions to ask?
Thanks, Xinyu. I do have a question about what's the status of tandem cell research at Jinko? Are you start looking at starting, or you just start, or yeah, just basically what's the status and what materials you're interested for TOPCon? Thanks.
All right. Well, tandem research is more like a little bit exploring type of project. So what I can comment is we have strong interest in tandem research, and also the potential application of tandem as well. And we do have projects going on this topic, but maybe too much details, I cannot comment too much. in terms of the materials and for the top cells, we look. One of the options is definitely perovskite. I think no one can avoid this topic, but from our point of view, we will not limit it by choosing perovskite only. We do see the option of other materials as well. Particularly, there are other space solar cell research institute or some like approaching us for collaboration. So definitely they won't be looking at perovskite for their main purpose. Yeah.
Okay, thank you.
Okay, I got a question from Michael. He's asking.
Yeah, I see the question.
You can see it, right?
Well. Yeah.
Okay.
So yeah, I think it's a very good question. So new materials include material applications for pretty much all possible areas. One good example I can mention is the surface passivating materials. So traditional surface passivating material has been developed and researched for decades and decades. So silicon nitride, aluminum oxide, or so we think these are sometimes a little bit out of date, and sometimes it's correlating to some troubles already, or including degradation or some other like IP issues. So we are thinking of new material as well. And the other materials such as the metal contact, we are also looking at the new materials potentially to solve this question. And as well as the module side, we do have new material projects going on with many parts such as encapsulation. And the encapsulation layers are like a multi-layer structure. So to control the multi-layer structure to find the best balance between cost and degradation. So it's also important direction. Also here the question also asking that the potential non-silicon based technology from I won't say this not Jinko starting from silicon is definitely our best best known area. So we're not expert in a non-silicon area, but we do have strong interests such as the thin film technology as well. One thing you've probably seen from the recent news that Jinko CEO is going to China's Lianghui, so the big meeting. So what he mentioned during the meeting is the potential for BIPV. So for BIPV, we do think silicon will play a major part of it, especially for some non-transparent applications. But still, there will be other applications for BIPV which requires leaning more to the non-silicon part. So we do have interest on this, but probably will be more cautious, more careful about the actual activities. Yeah. Hope that answers your question. Yeah.
Hope that answers your question, Michael. We might have time to take another question. Is anyone waiting for asking? Okay. If not, Xinyu, thanks for your talk. A lot of topics have been discussed during the seminar. Yeah, we can see that Jinko is doing well on the new technology. I looking forward to see when you next time visiting us to have another breakthrough. So thanks for the talk again, and thanks everyone listening to your talk and asking the question. I can see another chat. Okay, they are asking contact detail. I think Xinyu, you might answer this question in the panel. So as time is limited, we have to close the seminar today. thanks all people participating in the seminar and Xinyu for your talk. Thank you.